Have the next speaker.
Okay.
Yes, sir. Over to you. Over to you, sir.
Can you hear me?
Yes.
So I will share my screen. Let me check. Where is the Can you see it?
Yes,
yes.
but not in presentation.
Yes, I will change that in a moment. Sorry, close that space. Sorry. Oh. So it's okay now. Okay.
Yes.
So good morning to everyone. My name is Álvaro Folhas. I'm a Portuguese high school teacher and teacher training. I'm also a nuclear collaborator and a PhD student at the University of Coimbra. I will present an interdisciplinary experiment designed to work as an integrated natural sciences, physics, geography, and mathematics. Some curricular concepts about the 7th grade. First of all, the OECD Education 2030 highlights the need for students to acquire knowledge, skills, attitudes, and values that suit for the future demands. To make it possible, we must engage students to simple interdisciplinary approach to science education as a whole. But that's a very difficult task in our way to shape the school at the moment. So how to do it? For that purpose, I use astronomy because astronomy provides a unique platform to inspire students because it ties together different areas of knowledge from cutting edge technology to pure and applied sciences. But we need that for sure in our school to pursue the goals of the future. For that purpose, I try to design a teacher training program that involves a team of teachers, not just in the same area, but different areas that involve teachers that share the same classes of the 7th grade of Escola Básica Professor Artur Nunes Vidal. It's a school in the middle of Portugal. And I work with these 4 teachers to shape an activity that goes to the curriculum of these different areas with the same experiment. So some basic concepts. We know that at solar noon, the sun is in the highest position in the sky, crossing the meridian, casting the shortest shadow of the day. So Portugal is above, like we see it, is above the Tropic of Cancer. So in that moment, the shadow is precisely in the direction of the north, not the magnetic north, but the geographic north. So they can realize, not now because we just have a difference about 1 degree between the north magnetic pole and the north geographic pole. So, but in that sense, we can talk about that's not the same, and they will provide with this some experiments to realize for sure where is the North Pole. So for that experiment, we just have simple materials needed. like a nail. I use a nail, a sheet of paper, a compass, a watch, and some glue tape for that purpose. Measuring the vertical nail shadow, as you may see, in different times, we easily find the shortest shadow that point precisely to the north. We can keep also the length of the nail, and after that, with that, students must register all these values. They are able to work over that data to provide the different information for that fits in the curricula of the 7th grade in the different areas I mentioned before. So let's check what students have done. We at a very good starting point, we use stellarium to realize when solar noon occurs in our position and verify that the moment the sun is precisely in the highest position in the sky, crossing the 180 azimuth meridian, and the height of the sun at that time, the solar noon, should be noted by the students. They must be able to take that information to realize after, for the experimental approach, to realize if is very different or not from that values we have to find. So next, the experiment, they just have, they put the nail in the vertical, they measure the nail height, the nail distance, and they realize for the moment they mark in the paper all the shadows positions from during the time we have these measurements. After that, we have to realize that they start at least 1 hour before the solar noon, and after another hour after, to realize that the perception of the change of the size and the change of the orientation of the shadow is very important to the different approach we need to do. They check the shortest shadow and the time and figure it out the north direction. After that, measuring the nail and the shadow, they start to explore the analysis, finding the height of the sun and the angle of the shadow. They can do it. They don't have at this point the knowledge to make a trigonometric approach, but they can make the approach using making the triangle with that measurements and measuring with the what I don't know the name of this tool, the
protractor.
The protractor, of course. Sorry. So they, with that in mind, they find the height of the sun is 72 degrees. This is the same value they can reach if they use the trigonometric approach. To find the latitude from the spot, they can use the protractor with a straw. It's easy to do that, pointing precisely the Polaris star. They can use also a straw aligned with a smartphone with a inclinometer app. It's easy for them. Usually I try to use the schooler materials to give them another ways to be used as tools for other tasks. If we were at the equinox, it will be easy to find the latitude with that experiment at the solar noon, because with a similitude of triangles, they reach the angle. This beta angle is the same of the latitude. But we are not in that day. We are not in the equinox, so they need to make some correction to that value. And for that purpose, since we are not in the equinox, students must affect the process with the solar declination that oscillates from the equinox 23.5 degrees when we goes to the solstice of June, or minus 23.5 degrees when we goes to December. So the difference of the shadows with that can be corrected if they realize there is almost 90 days between these two marks. They can fix how much the position of the sun change from one day to another, and they must after that correct the number of days with that angle to make the right approach to find the latitude. The value we have reached is precisely 40 degrees, as you see here. That is a very good value because it's our latitude at the point we used to make this experiment. So students understood how to infer corrections to apply models to a reality that they know already. And what about not just the latitude? They can correct that way, and they can find also the longitude. How can they do it? They realize that regarding latitude, they know that a complete rotation of the Earth will be covered 360 degrees. So, and it takes 24 hours. So they can easily find how long it takes to rotate 1 degree. And it will be just 4 minutes for each degree. To obtain that by direct proportion, they use some concepts they have already learned in mathematics. After that, they goes to the stellarium at then this point, and they need just to check what time solar noon was in Greenwich, and it happens almost 1 p.m. So as you may see here. After that, they goes to our spot, and they realize the sun will be at the same meridian 34 minutes after. So 24 minutes after will be just knowing that we have 1 degree for each 4 minutes, they takes 8.6 degrees with that approach. So they reach also the longitude of the place. They have already know the latitude and the longitude, and for that they realize that not just numbers, they understand there is something about that numbers they can take for real. So they can verify these values and reach, they are very close to the spot they use the experiment. Can we do more with that? Of course we can. We can take the Eratosthenes experiment with that nail, as we may see. The Eratosthenes experiment use the Cyan and the Alexandria spots, and Eratosthenes take the shadow from the Alexandria that it takes 7.2 degrees, and he must know the distance between these two spots and make this proportion. They realize that is 50 times this distance to reach the entire Earth. So what must we do in this purpose? They take stellarium to realize in the same meridian what is the spot in Earth at solar noon will be the sun precisely in the zenith. And they took these coordinates, and with that coordinates, they realized what is the distance between these two spots using Google Maps, for instance. After that, with that in mind, they just have to make the calculations, the same calculations we mentioned before, and realize that the Earth, with that experiment, will have a 3,880 kilometers, that it makes an error, a relative error of 3%. It's a very good experiment, as we may see, to realize different tasks with the same experiment, mobilizing the concepts of mathematics, geography, physics, and also they take natural science to achieve where they can find the lichens in the trees, concerning that with the knowledge they have achieved from the north, the south, and so on. So the difference, I will make an assessment before and after the experiment, and we reach there is a statistical difference between before and after the experiment. They realize that we have 12.5% of improvement in the knowledge, just one activity they made in 2 hours, one day at least. But we realize we can do this share of knowledge, mobilizing concepts of geometry, about physics, about mathematics, about geography, that usually provide just one of each time. We can take that as a whole. That's what I intend to show. Sorry, I have to run the time quickly as I can. If you have questions, we will be glad to say something about.
Are there any questions? Yes.
I don't see any questions on Facebook.
Question
Álvaro,
from Paul Kraus.
Paul, yes, Paul, please.
I'm trying to, okay, it's here.
Hi,
Sorry.
Álvaro. Thanks for joining us. Great presentation. Congratulations. So my question is to your project. This extends the Aristophanes project, which if anyone hasn't tried it out there, please do. It's wonderful and for community collaboration. My question is, so relating to the mathematics, so I often find that some of the most difficult content to get across to students of the astronomy curriculum. Do you have any tips and tricks for engaging students, particularly in the mathematical side of our subject, and in particular regarding sort of sidereal synodic time, which my students still are concerned with the equation of time, and they struggle to comprehend why there's this difference between like local noon and actual time at UTC. Thank you.
This experiment was focused precisely about the curriculum of the 7th grade. So what is not in that area, I don't make this approach. The synodic time is not a subject we are working with, but even so, we can do the experiment to work that purpose, especially if we use it in different times in the year, to realize that the shadows, the declination of the sun, depends of the date, the about the time of the year we are doing. So we can, if we make the same experiment in different days, just to realize that and mark the values, we can achieve precisely the equation of time easily. Or if you want to do it, you can also to make some approach to showing that the shadows change along the year from the equinox to the solstice, and with that they can realize you can explore also the history, because the Portuguese maritime discoveries in the past using precisely these concepts to correct the position they made of the sun. Using the equation of time, there are some tables that can be used for that purpose also. So it can be feasible at using that kind of experiment. I try always do the experiments the easiest way I can, because usually schools says they don't have materials to do their approach, so I can use it with something they have all around to realize with the small things we can make big achievements.
Thank you, Álvaro. A brilliant response, as I knew you would be able to facilitate. Thank you, indeed, for your time and expertise.
You're welcome.
We have
We
also
have another question.
from Alan. Yes.
Yeah, it's a great activity. It's a whole array of activities, actually. I was wondering if you, and thank you for the presentation. I wonder if you address in the curriculum the ideas about the rate of change with the different seasons, because at this time of year, I'm especially aware and noticing, well, another aspect besides the elevation or the altitude angle of the sun is the sunrise and sunset positions and times that are at their maximum rate of change at around this time of year. And there's very little rate of change around the solstices. Is that something that you have ever addressed in the curriculum?
In this activity, I have some constraints because this is an activity for different disciplines, different areas. So I have to wait. The teachers have already teach the concepts that are involved in the experiment, because what I want to do is mobilize the concepts to make the students realize that not just something to be studied, but they can do lots of things with that. So I will make this experiment in June. So June, the shadow is the shortest. It's almost in the solstice. The error is maximum, and we don't have time enough to make another approach, just because it may one of these colleagues were sick in the hospital, so we have to move the activity to the end of the year. But it will be, because it's a very simple experiment, we can make it in different months to realize the position of the Earth around the sun is not the same, and they will change the way we feel the position of the sun in the sky during the year. I'm not sure if I'm straight to your question.
That's very good. I think I think part of the answer to my question could be that maybe Stellarium is the place to do that.
Stellarium is a very useful tool.
Yeah.
But if you use Stellarium and a physical experiment to realize the information provided by Stellarium is the same information they can took from the experiment, it gains much more enthusiasm for the students, and I suppose they will understand better the whole thing. That's what I intend to do.
Yeah, I'm getting a picture now that doing that activity, then what I'm talking about might be a follow-up using Stellarium once they have a vivid experience with it in the real world.
Yeah, I agree.
Thank you.
You're welcome.
We have also Facebook, Ivo Joaquim, send you congratulations and great work. We have some discussions here on the chat. But thank you, Álvaro, for making this. This was the last oral presentation of this conference, but we are not done yet. We'll have a break now, and when we come back, we have a workshop with Josina Nascimento and Jane de Fatima from Rio de Janeiro, and the closing remarks by Carl, Rosa, and everyone. So since we didn't have a presenter, we're having a slightly longer break, and we'll be back at 18:35 UTC. That's 23 minutes from now.